Hello, welcome to my talk on fluid motion description, Eulerian representation. In this talk, I will make a short summary of the Lagrangian representation, and then I will discuss what is the Eulerian representation for fluid motion, and then introduction of the substantial derivatives, and I will give an example for the applications of the Lagrangian and Eulerian method, and I will make more comparisons between these two methods. As we have mentioned, there are normally two different ways to describe fluid motion, that is, Lagrangian representation and Eulerian representation. In the Lagrangian representation, we chase the movement of all the fluid elements or particles. The fluid particle position is described by the vector RT with the three coordinates x, y, and z for each particle. And in the Lagrangian representation, the acceleration is simply calculated as this, the second order differentiation of the position vector r with regard to time. And on the trajectory of the individual particle, its coordinates x, y, and z are not independent. They all depend on time t. You can find all this in my talk on Lagrangian representation. But what is the Eulerian representation? This is the topic in this talk. First, we look at the flow passing airfoil. See this GIF. Generally, in Eulerian method, the fluid states, not the fluid particle trajectories, are our main interest. In the Eulerian representation, we divide the fluid domain, not the fluid itself, into many small spatial regions. See the rectangles in this plot. And the small region would be fixed in the fluid domain. For instance, the ith region would be determined by its coordinates xi, yi, and zi. And the coordinates x, y, and z for the small regions are independent parameters in Eulerian method. The fluid states are described use vector v x, y, z, t, or p x, y, z, t, or rho x, y, z, t in the regions. Now in this slide, we will look at the difference for the Lagrangian representation and the Eulerian representation. In the Lagrangian method, we divide the fluid into the element, see this particle, and we chase the movement of all fluid particles, see the particle in different time moving in the fluid. While for Eulerian method, we divide the fluid domain into the small regions, and all these regions will be fixed in the fluid domain. These are used for studying the fluid states in this region. For instance, how the flow passes the regions. Now suppose we have fluid velocity vector v in the Eulerian representation. This would be a main parameter for the fluid state in the fluid dynamics. Now we need to look at how we can use the velocity vector v to calculate the fluid acceleration. In fact, the fluid acceleration would be given simply as the acceleration vector A is defined as the differentiation of the velocity vector with regard to time. However, in Eulerian representation, the vector v would be the function of the coordinates x, y, and z, as well as time t. So v should be expressed as this. And we use the chain rule of differentiation. We can have the differentiation of the vector v with regard to time as this, the partial differentiation of the vector v with regard to time, plus these three extra terms. And we can write the partial differentiation of x with regard to t, y with regard to t, and z with regard to t. Use the velocity component vx, vy, and vz. So we have the fluid acceleration calculation in the Eulerian representation as this. This is called the substantial derivative for the fluid velocity vector v, or the material derivative. As used in many textbooks, the substantial derivative would be indicated using the capital D for the differentiation. Thus, it would be written as this capital dv vector divided by capital dt. So this will be given as this, the substantial acceleration. This part is called the substantial acceleration, and this is the local acceleration, and these last three terms are the convective acceleration. So in the Eulerian representation, the fluid acceleration is divided into two parts, as the local acceleration and the convective acceleration. And the convective acceleration is actually due to the velocity change along the streamline or the trajectory. So we can see here, the local acceleration is caused due to the velocity change over time in the region. And the convective acceleration is caused due to the velocity change along the streamline. From this expression, we see the partial differentiation of the vector v with regard to x is actually the gradient of the velocity vector v along x-axis. And this is an unusual expression for acceleration. But if we look at the unit for this term, we would have velocity and the position times the velocity. So we have the unit meter divided by second squared. This is the same as the unit of acceleration. In the Eulerian representation, the substantial derivative can be applied to other parameters or functions. For instance, for a scalar f, its substantial derivative is calculated as this. This is equivalent to the expression as this. This expression is a compact form of the expression, but the understanding of this form is more difficult since the very mathematical expression in here, the Leblanc operator in here. So in my talk, I will not use this compact form. I would like to use this clear form for better understanding. For a vector f, we have the expression as this, and the equivalent compact form would be given as this. And if we have an expression like rho vector v. So this is actually the linear momentum of the fluid per unit mass. So its substantial derivative is calculated as this, and the corresponding compact form would be given as this. In this slide, we will look at an important flow, a steady flow, the flow past an airfoil. For a steady flow, the mathematical equation is given as the partial differentiation of the vector velocity with regard to time. So what this means? This means for any given point, the velocity vector is constant, not changing with the time. But for different locations, the velocity can be different, like vector v1 compared to vector v. So they are very different in both direction and amplitude. For a steady flow, its substantial acceleration is generally not equal to zero. Since if we look at the flow particles, we can see the flow particles will change the speed and direction when it moves close to the airfoil. That means the substantial derivative of the velocity vector is not zero. A uniform flow is a special steady flow, and all these terms would be zero. The velocity is not changing with the time. The velocity is not changing with the location. However, for the substantial acceleration, if it is zero, what is the flow? So based on the expression, if each term in the substantial acceleration is zero here, then the substantial acceleration of the flow is zero. We can see some special flows for which the substantial acceleration would be zero. The first one is the uniform flow. For instance, Vx is constant as u0 and Vy equaling Vz equaling to 0. So we can check all these terms would be 0. Another example is the co-ed flow. So it is the flow between two large plates. The lower plate is fixed and the upper plate is moving with the velocity u0. And the velocity distribution would be given as this. So again, if we use all this velocity component into the substantial acceleration, we can see all terms in the substantial acceleration would be zero. And the example for the laminar pipe flow, Vx given as this, u0 is the velocity at the center of the pipe. Vy and Vz would be 0. So again, if we substitute this into the acceleration, we will see all terms in the substantial acceleration would be 0. Whether we have all these terms are not 0, but the summation would be 0. Mathematically, it is correct, but I have never seen such a flow. Now we look at the dynamic equation in the Eulerian representation. Look at the small region. Suppose its volume is delta v, and its velocity, the vector v. The fluid density is rho. Then the dynamic equation for the fluid in the region would be given as this. Here, this part is the mass of the flow, and this is the acceleration of the flow. This is the body force, for instance, the fluid gravitational force. This is the surface force due to the pressure and or viscosity. If the body force is the gravitational force, then the body force would be quite easy. However, the force due to the pressure, especially due to the viscosity, it's more complicated. So we can use the substantial acceleration, and the equation can be written as this. Here, the vector FB is defined as this. The vector Fs is defined as this. These two are the forces per unit mass. So this is the moment equation in the Eulerian representation. Now in the next few slides, I will use an example to show the difference between the Lagrangian representation and the Eulerian representation. The example is the falling ball. See this picture. This is similar to the water through a funnel. In the Lagrangian representation, we chase the position and the motion of each falling ball, and we can describe the ball position use zt in this case, and the velocity can be calculated as the differentiation of z with regard to time t. The acceleration at is calculated as the second order differentiation of zt with regard to t, or the differentiation of v with regard to time. So the dynamics of the falling ball in the Lagrangian method is given as this: m acceleration equaling to the force mg. Or the dynamic equation can be written as this. We can time dz to both sides of the equation. We have the expression as this. And on the left-hand side, we change dz and dv, so we have the expression as this. We notice dz over dt is actually the velocity, so we have the expression as this. And we integrate this differential equation. Consider the velocity be 0 when z is 0. So we have the expression as this. If we time the mass into the equation, we have the expression as this. This is actually the form of energy conservation between the potential energy and the kinetic energy of the falling ball. This is correct because in this problem, the air friction is ignored. And also, it should be noted, for this problem, since we have no surface force in the problem, thus the problem in Lagrangian method is solvable. So we have the result as the energy conservation form. Now we look at the same problem in the Eulerian representation. Here we study the velocity Vz1 at the reference point, say z equaling to z1 at point A. So this is very similar to the falling water through the funnel if we examine the water velocity at z equaling to z1. So obviously, the ball or the water passes the reference point z equaling to z1. The velocity is always the same. This means the velocity at the reference point is a constant independent of t. Thus, we have the partial differentiation of the velocity with regard to t is 0. This means in the Eulerian representation, the falling ball or the falling water through the funnel is a steady flow. And the substantial acceleration of the falling ball is calculated using the formula as this. Now we check the terms. The first term is 0, and in this problem, Vx, Vy would be both 0. Therefore, we have only one term left as this. Since the velocity vector has only one component, and it's the function of z only, therefore Vz is the same as v, and the partial differentiation of v with regard to z would be same as the normal differentiation v with regard to z. So this is the expression. Now put this together. So the substantial acceleration in the Eulerian expression would be given as this. So the dynamic equation in the Eulerian representation is given as this: mass times the substantial acceleration equaling to the force acting on the falling ball, mg. So this is equivalent as this, since the substantial acceleration in this special problem can be represented by this expression. So we have the equation as this, and we integrate this equation by considering the velocity is 0 when z is 0. So we have the expression as this, and time the mass of the ball into the equation. We have the same energy conservation form as we have obtained in the Lagrangian representation. So we can see for the same problem, we can use either Lagrangian representation or the Eulerian representation. We obtain the same form of the energy conservation between the potential energy and the kinetic energy. Now we have a look at the summary of the fluid motion description. In my last talk, the Lagrangian representation has been taught. So it is a method for tracing the movement of all the fluid elements or particles. And the fluid particle position is described by the coordinates xt, yt, and zt. And for each individual element, its coordinates on the trajectory x, y, and z are not independent. They all depend on time. While in this talk, the Eulerian representation is introduced. So this method examines the fluid field or state at the reference point. The coordinates for the reference point would be given by xi, yi, and zi for the ith region. And the coordinates x, y, z are the independent parameters. That is, when x is given, y and z can still be decided independently. And the fluid field or states are described. Use vector v, x, y, z, and t, the pressure p, x, y, z, t, and the density rho, x, y, z, t, etc. For these two expressions, the acceleration is calculated in different way. In the Lagrangian representation, the vector A is calculated as the second-order differentiation of the vector r with regard to time t. Or we have the component ax given as the second-order differentiation of x with regard to time, and so on. While in the Eulerian representation, the acceleration is calculated given as this: the substantial acceleration in the Eulerian representation, and the component given as this. So we can see for the motion expression, Lagrangian representation is simpler. Since the acceleration is linear in expression, the normal second-order differentiation with regard to time. While the acceleration in the Eulerian representation is nonlinear in the expression, much more complicated for the convective acceleration in this rectangle. Here we compare the dynamics, the momentum equations in Lagrangian representation and the Eulerian representation. In Lagrangian representation, the dynamic equation would be given as this. Here, the force vector Fb and the vector Fs would be the forces per unit mass. And if we write the equation for the component, we could have the equation as this. However, if we look at the dynamic equation in the Eulerian representation, the expression should be given as this, or the component form for the momentum equation given as this. Superficially, the momentum equation in the Lagrangian representation seems much simpler, while the momentum equation in the Eulerian representation are much more complicated. Then, we may ask a question, why in fluid dynamics, Eulerian method is mostly used? To answer this question, we can say, generally, the fluid dynamics is indeed very complicated, especially for the turbulent flows. Thus, there should be no easy ways to solve the problem. As we see many times, fluid dynamics, or the turbulent flows, remains unsolved in the classic physics. Superficially, the Lagrangian representation would have simpler dynamics equation because of the linear accelerations. Can we say we can solve the complicated fluid problem in the Lagrangian method? The answer for this is no, because in the Lagrangian representation, the difficulties for the complicated flows are actually in the force calculations. It is very complicated, and in some cases, it is impossible. The main issue with the Lagrangian representation is that the coordinates x, y, and z on the trajectory of the fluid particle motion are not independent. This causes the huge difficulties in formulating the surface forces. In fact, the dynamic equation for 3D viscous flows in the Lagrangian representation is still an open question. This means we don't have the dynamic equation for the 3D viscous flow in the Lagrangian representation. The other problem for the Lagrangian method is for chasing all the fluid elements or particles in the fluid would be much more complicated and demanding than those fixed small regions in the Eulerian representation. And this is the problem for the very complicated problem. Chasing all these fluid element particles in the fluid would be beyond the current computer capacities.